Imagine you are a geologist. You have spent decades studying mountains, cataloging them, mapping them, understanding the forces that shaped each individual peak. You know this mountain range intimately. You know every valley, every glacier, every fault line. You have published papers about individual summits. You have stood at the base of each one and looked up with the quiet satisfaction of someone who knows exactly what they are seeing. And then, one morning, a satellite image arrives on your desk, and in the image, you see something that stops your breath entirely. Those are not separate mountains. That is one wave. One single, enormous, continuous wave, frozen in stone, stretching further than you ever imagined possible. Every mountain you studied, every valley you named, every paper you published, all of it was a fragment of something so vast that the human eye, standing at the base of any individual peak, was physiologically incapable of seeing the whole picture. You were so close to each tree that you never saw the forest. You were so intimate with each chapter that you never once held the book. This is not a metaphor. This is almost precisely what happened to a team of astronomers at Harvard University in the year 2020. For decades, scientists had catalogued what they called molecular clouds, dense regions of cold gas and cosmic dust scattered throughout the spiral arm of the Milky Way galaxy nearest to our solar system. The Orion Molecular Cloud, the Perseus Molecular Cloud, Taurus, Ophiuchus, Lupus. Each one was mapped, studied, named, treated as its own isolated structure floating independently in the vastness of interstellar space. Each one was believed to be its own story, a separate chapter in the encyclopedia of the galaxy, with its own origin, its own dynamics, its own eventual fate. Generations of astronomers built entire careers studying these objects. Conferences were held in their name, textbook chapters were written, maps were drawn. The picture of our local galactic neighborhood, assembled piece by piece across a century of careful observation, seemed not complete because science is never complete, but reasonably well established. We knew the landmarks, we knew the neighbors. We believed we understood the general shape of the territory we inhabited. Then a team led by astronomers Alyssa Goodman and João Alves sat down with data from the European Space Agency's Gaia satellite, a spacecraft that has been measuring the precise three-dimensional positions and motions of nearly 2 billion stars with a level of accuracy that previous generations of astronomers would have dismissed as science fiction, and did something deceptively, almost insultingly simple. They mapped those molecular clouds not as flat, two-dimensional objects projected onto the surface of the sky, as astronomers had been doing for a century, but as real three-dimensional structures occupying genuine positions in actual three-dimensional space. And the moment they did that, something broke. Not the data, the model. Because when you arrange those supposedly separate, supposedly independent clouds in true three-dimensional space, when you stop flattening them against the background of the sky and actually position them where they genuinely exist in the galaxy, they are not separate at all. They form a single, continuous, coherent structure, a structure that stretches without interruption for approximately 9,000 light-years. A structure that undulates, that rises and falls rhythmically and gracefully like a wave in water, in a pattern so regular, so mathematically precise, that the probability of it being coincidental is essentially zero. They called it the Radcliffe Wave, named after the Radcliffe Institute for Advanced Study at Harvard, where the research was conducted. And from the moment that name was given, the map of the galaxy we thought we knew, refined and corrected and improved across more than a century of modern astronomy, was fundamentally, irreversibly incomplete. We had been studying the fingers of a hand and calling each finger a separate creature. We had never once stepped back far enough to see the hand. The question that should stay with you, the question that should follow you out of this video and persist in the back of your mind for days is not what the Radcliffe Wave is. The question is, what else have we been unable to see? What other hands are out there, invisible to us not because we lack the instruments to detect the individual components, but simply because we have never had the perspective required to recognize the whole. The universe does not announce its architecture. It does not leave instruction manuals. It does not flag its structures with labels or warning signs. It simply exists in its full staggering complexity and waits with infinite and entirely indifferent patience for something clever enough and humble enough to eventually look at it the right way. We have been looking at the galaxy for centuries. In 2020, for the first time, we finally looked at it the right way, and the galaxy looked back. Before we go any further into the physics and the mechanics of what was discovered, we need to stop. We need to genuinely, honestly, uncomfortably reckon with the scale of what we are talking about. Because human beings are profoundly, structurally bad at this. We are not built for cosmic scales. Our brains evolved to navigate a savanna, to track prey moving at 30 kilometers per hour, to gauge distances measurable in tens of meters, to plan across time horizons of days and seasons. The universe operates on none of these scales. The universe operates on scales so different from our daily experience that honest comprehension of them, if done correctly, with real intellectual honesty and no protective padding of abstraction, should produce something very close to vertigo. So let us begin with something you can hold. Pick up a ruler, a standard 30-centimeter ruler, the kind that lived in your school pencil case. Hold it in your hand, look at it. The distance from one end of that ruler to the other, 30 centimeters, represents the distance light travels in approximately 1 nanosecond, 1 billionth of 1 second. Light is the fastest thing in the known universe. It travels at approximately 300,000 kilometers per second. If you could wrap a single beam of light around the Earth's equator, a journey of nearly 40,000 kilometers, that beam would complete the full circuit approximately 7.5 times in a single second. 1 light year, the distance light travels in 1 full Earth year, is approximately 9.5 trillion kilometers. 9,500 billion kilometers. Write that number out with all its digits and stare at it. Now multiply it by 9,000. That is the length of the Radcliffe Wave. 9,000 years of travel at the fastest speed anything in this universe is permitted to move. Not merely the fastest speed achievable with current human technology, but the absolute cosmological speed limit, the maximum velocity permitted by the geometry of space-time itself. If humanity had launched a spacecraft moving at the speed of light, which the laws of physics forbid, which special relativity makes impossible for any object possessing mass, at the exact moment our earliest anatomically modern ancestors were learning to shape stone tools on the plains of Africa, that spacecraft, right now, at this precise moment in history, would still not have reached the far end of the Radcliffe Wave. But abstract numbers, however staggering, tend to slide off the surface of the mind without leaving a real mark. So let us try a different approach. You live, whether you know it or not, inside something called the local bubble. The local bubble is a vast, irregularly shaped region of space, an enormous cavity carved into the interstellar medium of the Milky Way, that was hollowed out by a series of supernova explosions occurring approximately 14 million years ago. The dying stars that created it, perhaps 15 of them, perhaps more, detonating in sequence across millions of years, blasted their surrounding gas and dust outward in great expanding shells, and where those shells swept the region clean, they left behind an enormous emptied pocket of relatively sparse hot plasma. The sun, along with every single star in our immediate cosmic neighborhood, every star you have ever seen with the naked eye on a perfectly clear night, exists inside this bubble. We are all passengers inside the same ancient cavity, carved by explosions that happened before our species existed, moving slowly through a pocket of the galaxy that dead stars cleared for us. The diameter of the local bubble is approximately 1,000 light-years. A distance so vast that the concepts we normally use to measure things, kilometers, miles, the circumference of the Earth, the distance to the Moon, collapse into complete irrelevance. The Radcliffe Wave is approximately 400 times larger than the local bubble. 400 times. If the local bubble were represented by a single grain of sand, one small, unremarkable grain of sand held between your fingertips, then the Radcliffe Wave, drawn to the same scale, would be roughly the length of your forearm. And the Radcliffe Wave is not the Milky Way. The Radcliffe Wave is one structure within one spiral arm of the Milky Way. One wave, one ripple, in one galaxy. The Milky Way contains somewhere between 100 and 400 billion stars. There are estimated to be somewhere between 200 billion and 2 trillion galaxies in the observable universe alone. The universe as visible from our location, bounded by the cosmic horizon, the distance beyond which light has not yet had time to reach us since the Big Bang. We are smaller relative to the observable universe than a single atom is relative to the entire Earth. Not approximately, not as a poetic metaphor. Mathematically, precisely, sit with that. Think about the civilization you are part of, the cities, the nations, the entirety of recorded human history with all its wars and discoveries and art and love and ambition and grief, every book ever written, every structure ever built, every human life ever lived, from the first fire to the last satellite signal. All of it exists on a pale blue dot that is, from the perspective of a hypothetical observer standing at the far end of the Radcliffe Wave, not visible to the naked eye, not small, not dim, genuinely not visible at all. We are not small the way an ant is small relative to a human. We are not small the way a bacterium is small relative to a mountain. We are small in a way that the word small genuinely cannot contain. Small in a way that our language, which evolved to describe a world of human-scale objects moving at human-scale speeds across human-scale distances, structurally struggles to articulate. And yet, we found the Radcliffe Wave. We found it with instruments built by human hands, guided by mathematics developed by human minds, fueled by observations collected across human lifetimes by human patience and human stubbornness, and the fundamentally, almost maddeningly human refusal to stop asking why. There is something in that worth sitting with. A candle is small, absurdly, almost comically small in the scheme of things, and yet a candle, in a dark enough room, is visible from the other side. Our smallness does not determine our reach. Our smallness does not determine the outer boundary of what we are capable of perceiving or understanding. We are small, and we noticed a 9,000 light-year wave. That is, arguably, the most remarkable sentence in this entire story. Now let us talk about what the Radcliffe Wave actually does. Not just its size, its behavior, its nature as a dynamic object in the living galaxy. Because in 2024, 4 years after the initial discovery of the structure, a team of astronomers published a paper that did not merely confirm what Goodman and Alves had found. It revealed something far more unsettling about the fundamental nature of what they had found. Something that should rewrite, quietly and permanently, the way you picture our galaxy. The Radcliffe Wave is not static, it moves. Let me be precise about what this means because the word moves is somewhat misleading in an astronomical context. Everything in the galaxy moves. The sun moves. Every star, every cloud of gas, every grain of interstellar dust is in constant motion, orbiting the center of the Milky Way on great arcing paths, drifting relative to its neighbors in the endlessly churning ensemble of the galactic disk. When astronomers say the Radcliffe Wave moves, they do not simply mean it orbits the galactic center along with everything else. They mean something more specific, something more extraordinary, something that, once you understand it, makes the Milky Way feel less like a backdrop and more like a living sea. The Radcliffe Wave oscillates, it ripples, it undulates. It physically rises and falls, moving perpendicular to the flat plane of the galactic disk in a rhythmic, wave-like motion as regular as a metronome, as vast as the distance between entire constellations. Like a rope being shaken steadily at one end, sending a wave traveling down its entire length in perfect sequence. Like the surface of the deep ocean rolling under a long oceanic swell that began thousands of kilometers away. Like a flag suspended in a steady, constant wind, its full length undulating in beautiful synchrony at once. We are accustomed, because every representation of the galaxy we have ever seen reinforces this, to thinking of the Milky Way as essentially flat, a disk, a cosmic frisbee, a giant pinwheel spinning steadily in 2 dimensions. And yes, broadly speaking, this is a reasonable first approximation. The Milky Way is a disk-shaped structure, and most of its stars and gas are concentrated in a relatively thin plane. But the plane is not perfectly flat, and the Radcliffe Wave is proof of this in the most dramatic possible way. The wave extends above and below the galactic midplane, the theoretical perfectly flat line running through the mathematical center of the disk by approximately 500 light-years on either side. The crest reaches 500 light-years above the galactic plane. The trough plunges 500 light-years below it. And the entire structure oscillates between these extremes on a timescale of approximately 70 million years. One complete rise and one complete fall across 70 million years of cosmic time. Let us pause on that number. 70 million years for one oscillation. The last time the Radcliffe Wave was in the exact configuration it occupies right now, the Cretaceous period on Earth was reaching its violent conclusion. The Chicxulub impactor was about to strike what is now the Yucatan Peninsula of Mexico. The non-avian dinosaurs, which had dominated the Earth for more than 150 million years, had perhaps days or weeks left as the ruling vertebrates of this planet. The ancestors of every mammal currently alive, every human being, every elephant, every whale, every mouse, were small, warm-bodied, largely nocturnal creatures, hiding in burrows and beneath undergrowth. Their entire neurological architecture tuned entirely to moment-to-moment survival, utterly incapable of contemplation. And the Radcliffe Wave was occupying the same phase of its oscillation cycle it occupies today. Now here is where the story becomes genuinely, uncomfortably personal. Our solar system is not currently inside the Radcliffe Wave. We sit beside it, close enough that many of the nearest stars in our galactic neighborhood are members of it, close enough that the wave has profoundly shaped the interstellar environment of our cosmic home. But we are not inside it right now. We were. Approximately 13 million years ago, at a moment in Earth's biological history when the planet was inhabited by early hominoids beginning the long evolutionary journey that would eventually produce us, when the first species on the direct ancestral line toward modern humans were beginning to emerge in the African forests, our solar system was passing through the Radcliffe Wave. We drifted through it as the galaxy slowly turned and the wave slowly oscillated. We were inside it the way a sailing ship is inside a region of great ocean swells, surrounded on all sides by the structure, immersed in its medium, part of its environment in the most complete and literal sense. For millions of years, the Radcliffe Wave was not something distant, not something out there across the galaxy, not something to be detected and mapped and named. It was here. It surrounded us. Its molecular clouds were the nearest concentrations of gas and dust in the interstellar medium. Its structure was the context of our solar system's existence in the galaxy, the neighborhood, the medium, the cosmic address. And then, gradually, as the galaxy turned and the wave oscillated and the solar system followed its own orbital path, we drifted out. We left the wave behind. And now, we look back at it from the outside. The way an adult might look back at a childhood landscape that shaped them without their ever knowing it. The confirmation that the wave is genuinely oscillating, published in 2024, relied on measuring not just where things are in space, but how they are moving through it. Researchers used data from the Gaia satellite to measure the velocities of young stellar associations, tightly bound groups of stars so recently formed that they almost certainly coalesced from the gas of the Radcliffe Wave itself within the last few million years. These stars, being young enough to still carry the kinematic signature of their birth environment, preserve in their motions a kind of frozen memory of the wave's velocity at the moment of their formation. Stars born within the wave carry the wave's perpendicular motion with them, like a surfer who, after riding a great wave, continues moving in the same direction even after the wave itself has passed beneath them and rolled on. By measuring the vertical velocities of these young stellar associations with the extraordinary precision enabled by Gaia, the team demonstrated conclusively that the Radcliffe Wave is not merely an undulating static shape, but a genuinely propagating physical wave, carrying energy through the interstellar medium of the galaxy at this exact moment, right now, as you sit and listen to these words. This distinction matters more than it might initially seem. A static shape that undulates is simply a complicated mountain range, unusual, perhaps beautiful, but passive, inert, a monument to some ancient force rather than an active participant in the present. A propagating wave is an entirely different kind of object. It carries energy. It transfers that energy to whatever it encounters. It interacts with its medium in ways that a static structure cannot. It is, in the truest physical sense of the word, alive, not biologically, but dynamically. The Radcliffe Wave is carrying energy through the disk of the Milky Way right now. And here is what this forces us to confront. The Milky Way we thought we knew, the slowly rotating, largely static, roughly pancake-shaped disk, its spiral arms gently trailing behind its rotation, its stars orbiting in approximately circular paths, its structure ancient and settled, is not the Milky Way that actually exists. The Milky Way that actually exists is a dynamic, churning, oscillating system disturbed by forces operating on time scales and distance scales that make all of human history seem like a flicker of static between broadcasts. It is alive in the sense that a storm-tossed sea is alive, in the sense that a vibrating string is alive, filled with waves and oscillations and propagating disturbances, interacting and carrying their energies across distances that genuinely beggar the imagination. The Radcliffe Wave is almost certainly not the only such structure in the Milky Way. It is the one we found first, the closest one, the one whose molecular clouds we had been studying in careful detail for decades without ever asking the right three-dimensional question about their arrangement. Almost certainly, structures of similar nature and similar scale exist throughout the disk of the galaxy and throughout other galaxies. We have found one. We have opened the catalog, and the catalog has precisely one entry. What will 10 entries look like? What will 100 entries teach us? The galaxy is not the thing we thought it was. It never was. We were simply looking at it from too close. The discovery of the Radcliffe Wave immediately raised the question that every honest scientist working in this field will tell you remains, as of this moment, genuinely unanswered. What caused it? What force? What event? What combination of physics and history and cosmic coincidence set a 9,000 light-year structure into this steady, majestic 70 million year oscillation through the plane of the Milky Way? The answers currently on the scientific table range from the familiar and plausible to the profound and the genuinely, quietly unsettling. And each answer, in its own way, says something important not just about this specific structure, but about the kind of universe we inhabit. Begin at the conservative end. The most straightforward explanation, the one requiring the fewest extraordinary assumptions, the one most easily reconciled with things we already know, involves a collision. The Milky Way is not alone in space, and it has a history of violent interaction. It belongs to the Local Group, a gravitationally bound collection of galaxies dominated by two large spirals, our own Milky Way and the Great Andromeda Galaxy, along with dozens of smaller satellite and dwarf galaxies orbiting at various distances. Those smaller galaxies do not orbit at safe, respectful distances, maintaining polite gravitational separation from the systems they attend. They fall inward, they merge, they pass through, and when they do, they leave gravitational disturbances behind, ripples propagating outward through the disk, the way a stone thrown into a pond leaves rings expanding outward long after the stone has settled to the bottom. The Sagittarius Dwarf Galaxy, a small satellite galaxy that has been slowly spiraling inward toward the Milky Way across billions of years, periodically plunging through the galactic disk and being partially absorbed in each encounter, stands as one of the leading candidates for having triggered the Radcliffe Wave. Current orbital modeling suggests the Sagittarius dwarf has made multiple close passes through the Milky Way's disk over the past few billion years. Each passage would have sent gravitational disturbances propagating outward through the disk, building up oscillatory modes that could, in principle, explain the wave-like structure we now observe. The timing of certain proposed passages aligns, at least approximately, with the apparent dynamics of the Radcliffe Wave. This hypothesis has genuine explanatory power. It connects the wave to a known event in galactic history, and as our modeling improves, it becomes increasingly testable. A second, more localized version of the collision hypothesis focuses not on a dwarf galaxy, but on a high-velocity gas cloud, one of the enormous concentrations of infalling material that exist above and below the galactic disk, raining down onto the Milky Way from the surrounding intergalactic medium, or falling back after being expelled by ancient supernova-driven outflows. A sufficiently massive high-velocity cloud striking the disk at the right location and the right time could have created exactly the localized hammer blow that would send a ripple propagating outward through the interstellar medium. A stone dropped onto a drumhead, an impact point, and an expanding ring. These collision hypotheses are reasonable. They invoke known phenomena. They explain the basic existence of the oscillation. But there is a feature of the Radcliffe Wave that they struggle to fully account for: its coherence. A ripple in a pond does not maintain perfect regular oscillation indefinitely. It dissipates. It loses energy to friction and turbulence and the irregular structure of the medium through which it moves. It becomes disordered and eventually fades. The Radcliffe Wave, across 9,000 light-years and across what appears to be multiple oscillation cycles, maintains remarkable regularity, remarkable structural coherence. This persistence of organized wave structure across such vast distances and such vast timescales is difficult to explain purely through a single impulsive external event, which brings us to the more radical end of the spectrum: dark matter. Approximately 27% of the total energy content of the universe, by the best current measurements, consists of dark matter, a substance, or perhaps a collection of substances, that does not interact with light, emits no radiation detectable by any current instrument, and reveals its existence solely through its gravitational effects on the ordinary matter that astronomers can see. Its existence is inferred from the way galaxies rotate faster at their edges than visible matter alone could explain, from the way light bends around galaxy clusters far more strongly than their visible mass would predict, from the large-scale distribution of matter in the universe, from the precise pattern of temperature fluctuations in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space in every direction. Ordinary matter, atoms, molecules, everything you have ever seen or touched or measured, every star ever catalogued, every galaxy ever photographed, makes up approximately 5% of the universe's total energy budget. Dark matter outweighs us by more than 5 to 1, and we cannot see any of it. The dark matter associated with the Milky Way does not form a disk like the stars and gas. It forms a vast, diffuse, roughly spherical halo surrounding the disk and extending far beyond it in every direction. A dark gravitational shell whose total mass is estimated at approximately 1 trillion times the mass of the Sun, invisibly dominating the gravitational environment of the entire galaxy. That halo is not smooth, but it has structure. It almost certainly contains sub-halos, smaller concentrations of dark matter orbiting within the larger halo, remnants of dwarf galaxies absorbed long ago, stripped of their visible stars by tidal forces but retaining their dark matter component, effectively invisible to every telescope we have ever built, yet gravitationally massive enough to matter. A sufficiently massive dark matter subhalo passing near or through the galactic disk would exert gravitational forces on the gas and stars in that disk. It would perturb them. It would displace them. It would potentially trigger exactly the kind of oscillatory wave we observe in the Radcliffe Wave. And then, through continued gravitational interaction as the subhalo continued on its orbital path, potentially sustain and maintain that oscillation over timescales far beyond what a single impulsive event could produce. This hypothesis is physically plausible. It is consistent with what we know about dark matter halo structure. It is, in principle, testable through careful study of stellar kinematics and disk dynamics, and it may never be definitively confirmed. Because the thing it invokes as its cause cannot, by definition, be directly detected by any instrument we could conceivably build, we would be confirming the existence of an invisible object by measuring the disturbance it left in visible matter, like trying to determine the shape of a ghost by studying the impression it left in a mattress. We are trying to understand a structure possibly caused by something we cannot see, using instruments designed to detect things that interact with light. There is a third hypothesis, quieter than the others, no less profound. The galactic disk is not merely a collection of independently orbiting objects. It is a dynamically coupled system in which all the stars and gas interact gravitationally with each other in a collective way. And this collective self-gravity can support large-scale coherent oscillations, what theorists call bending waves or corrugation waves, propagating across the disk as a whole, driven and sustained by the disk's own physics rather than by any external trigger. If the Radcliffe Wave is a manifestation of such a bending wave, if it is a local expression of a galaxy-wide oscillatory mode triggered by some large-scale perturbation and then propagating and sustaining itself through collective galactic self-gravity, then it is not a local anomaly in the Milky Way. It is a property of the Milky Way, a fundamental feature of how the galaxy behaves as a physical system. It would mean we are not merely watching a ripple left by some ancient impact. We are watching the galaxy breathe. These hypotheses are not mutually exclusive. The wave may have been seeded by an impact, a dwarf galaxy, a high-velocity cloud, an invisible dark matter subhalo, and that initial disturbance may then have excited a pre-existing bending mode of the disk, which then amplified and sustained the oscillation far beyond what the initial event alone could have produced. Reality, at galactic scales, rarely reduces to a single cause with a clean, simple explanation. What matters is this: we do not know. And the not yet knowing is not a frustration. It is the frontier. It is the precise location where the most important work in modern astrophysics currently happens. The honest scientific answer, as of today, is that we have a structure of extraordinary scale and extraordinary dynamics, and we have several hypotheses that can each explain parts of what we observe, and none that fully explains all of it, and the investigation continues. That is not a failure. That is exactly where you want to be. 13 million years ago, our solar system was inside the Radcliffe Wave. The Sun, moving along its orbital arc around the galactic center, was embedded in the dense molecular clouds that make up this structure. The interstellar medium surrounding our solar system was the wave's medium. The gas and dust filling our immediate cosmic environment was the wave's gas and dust. For millions of years, if some being had looked up from any world orbiting any star in our solar system's neighborhood and asked where they were in the galaxy, the true honest answer would have been, inside a 9,000 light-year wave, currently mid-oscillation. 13 million years ago, our ancestors were small primates in the forests of Africa. Their lineage had recently diverged from the common ancestor we shared with chimpanzees. Their cognitive architecture was nowhere near capable of abstraction, nowhere near capable of language, nowhere near capable of wondering about the structure of the galaxy. They were alive in the most immediate, unmediated sense, eating, moving, watching, responding, surviving in each moment as that moment arrived, without past, without future, without cosmos. We are the descendants of those creatures. We are the ones who eventually, through an improbable sequence of evolutionary pressures and climatic accidents and competitive struggles spanning millions of years, grew brains large enough for abstract thought, flexible enough for language, persistent enough to accumulate knowledge across generations, ambitious enough to build telescopes and satellites and mathematical frameworks, curious enough to ask not merely where am I right now, but where is my solar system in the galaxy, and where was it 13 million years ago, and what was it moving through? We found the wave, not because the wave announced itself, not because it was obvious, not because the answer was waiting on the surface to be skimmed off with a casual glance. We found it because the Gaia satellite was conceived and designed and launched and operated across decades by thousands of human beings dedicating their working lives to the project. Because a team at Harvard had access to that data and asked the right geometric question at the right moment. Because the answer was there, waiting in 3 dimensions, waiting for the first mind that would look at the old data from the right angle. We found it the way all the genuinely great things in science are found, by building the tools with patience and operating them with precision and being willing, genuinely willing, with no protective attachment to existing models, to have everything you thought you knew broken by what the data reveals. But the discovery of the Radcliffe Wave did not close a chapter in astronomy. It opened one. It took a relatively settled, relatively comfortable picture of the local galactic neighborhood and replaced it with a more complex, more dynamic, more beautiful, and more bewildering picture that immediately generated more unanswered questions than it resolved. Before 2020, we thought the molecular clouds of the Perseus and Orion regions were understood objects in an understood environment. We thought we had, broadly speaking, a working picture of the territory. We were wrong, not through carelessness, not through lack of effort. We were doing the best work we could with the tools and the perspective available to us. We were wrong in a way that is deeply characteristic of how knowledge advances at its frontier. not through the gradual accumulation of details within a stable established framework, but through sudden, vertiginous, perspective-shifting realizations that dissolve the old framework and demand the construction of an entirely new one. This has happened before. Many times. It will happen again. Every generation of scientists inherits a map of the universe from the generation that came before it, and every generation, armed with better instruments, better data, better mathematical tools, better perspective, discovers that the inherited map is wrong in some fundamental way. Not wrong in the sense of being useless. The old maps serve as foundations, but incomplete, in ways that cannot be corrected simply by adding more detail to the existing structure, but only by stepping back far enough or looking from a different angle to see what the existing structure has been systematically missing. The Radcliffe Wave was invisible to a century of professional modern astronomy, not because astronomers were not looking, not because the instruments were too weak. The individual components were detected. Their properties were measured accurately. It was the arrangement that was missed, the three-dimensional geometry that was never examined because the right question had never been asked. How many other structures are invisible to us right now for the same reason? What other answers are hiding in the data we already have, waiting not for more powerful instruments, but for a different angle of approach, a different dimension of interrogation, a different question? This is what the Radcliffe Wave points toward, not just its own specific physics, which are extraordinary and important, but a more general, more humbling lesson about the relationship between knowledge and perspective. The universe is not a puzzle with a finite number of pieces that will someday be assembled into a complete and final picture. It is a structure that reveals new layers of organization at every scale at which you examine it, not because complexity is being generated to stay ahead of your instruments, but because the complexity was always there at every scale. And each improvement in our ability to look simply allows us to perceive one more level of what was always present. Seen at the scale of individual atoms, matter is a collection of particles. Seen at the scale of molecules, it becomes chemistry. Seen at the scale of cells, it becomes biology. Seen at the scale of individual stars, the Milky Way is a collection of isolated burning spheres. Seen at the scale of stellar associations, it is a system of loosely grouped families of related stars. Seen at the scale of molecular clouds, it is a scattered field of dust and cold gas. And now, seen at the scale of thousands of light years in 3 dimensions, it is a system of enormous oscillating waves, rising and falling through the galactic disk with a patience that makes the entire history of animal life on Earth seem like a brief morning. There is always another scale. There is always a larger context. There is always a perspective from which the familiar resolves into something unrecognizable, something more intricate, something grander, something that makes the previous picture seem like a rough sketch made in dim light by someone standing too close to the canvas. The Radcliffe Wave is oscillating right now. It has been oscillating since before the genus Homo existed, since before our lineage separated from the other great apes, since before the first stone was napped into a tool by hominid hands, since before the first intentional fire was lit. It will be oscillating long after every trace of our civilization has been dissolved by time, long after the last city has been returned to geology, long after the last satellite has drifted out of orbit, long after the last molecule carrying any chemical memory of our existence has been recycled into the interstellar medium. The wave does not know we are here. It is not magnificent in the sense that it intends to be magnificent. It is not ancient in the sense that it is trying to make us feel small. It simply exists, governed by the laws of physics, operating at scales for which those laws produce consequences our intuitions were never built to accommodate, oscillating with the same steady rhythm, whether or not any mind in the universe is watching. and we are small. We are astonishingly, almost vertiginously small by comparison. The entire documented history of human civilization, from the first writing systems to the most recent scientific discovery, would occupy a fraction so tiny of one oscillation cycle of the Radcliffe Wave that representing it accurately on any graph would require a line thinner than any physical line that could be drawn. But here is the thing. Here is the thing that matters. The thing that should stay with you after this video ends and you return to the ordinary human world of rooms and streets and distances you can actually feel. Consciousness is, as far as we know, the universe's only mechanism for knowing itself. We are not observers of the cosmos standing safely outside it, watching through glass. There is no outside. We are part of the universe, temporary configurations of the same matter and energy that makes up molecular clouds and stellar associations and oscillating galactic structures and dark matter halos. We are made of atoms forged in dead stars. We carry in our bodies the chemical legacy of billions of years of stellar and planetary history. We are not separate from the cosmos, looking in. We are the cosmos, in one very small and very temporary configuration, looking at itself. And what it sees, when it builds careful enough instruments and asks careful enough questions, is a 9,000 light-year wave rippling through the disk of a galaxy, carrying the memory of a collision or a perturbation that happened before human beings existed, oscillating with a regularity that makes all of recorded history seem like a single heartbeat in the life of a giant. And that wave, 13 million years ago, was here, right here, where you are now, where this planet has always been, moving with the sun through the slow turning of the galaxy. The Radcliffe Wave passed through our cosmic address and left, and now we have looked back across 13 million years of distance and found it again. We have reconstructed where it was and what it was doing, and that we moved through it. We have measured the ghost of our own passage. The universe does not reveal its nature all at once. It has never revealed its nature all at once. It delivers understanding in fragments, a molecular cloud here, a stellar velocity there, a data set from a satellite measuring nearly 2 billion stars with extraordinary patience, and it waits for the minds capable of assembling those fragments into something coherent, into something that resembles a picture, into something that earns the word understanding. We are, right now, at the very beginning of assembling that picture, not near the middle, not approaching the end. At the beginning. Everything we know about the structure of the Milky Way, all the maps, all the models, all the papers, all the textbook chapters, represents the state of understanding of a civilization that has had access to genuinely powerful astronomy for, at most, a few human generations. A civilization that discovered only recently that the universe is expanding, that other galaxies exist, that the Big Bang happened, that dark matter outweighs visible matter, that the expansion of the universe is accelerating due to something we call dark energy, and understand essentially not at all. We are an infant civilization staring at an adult universe, and occasionally, when the light falls right and the instruments are pointed in the right direction and someone asks the right question, we glimpse something so much larger than ourselves that it should honestly leave us speechless. The Radcliffe Wave is not an answer. It is an invitation to keep asking, to keep building instruments and operating them with patience and reading the data with honesty, to keep looking at the galaxy from new angles, armed always with the knowledge that every map we have ever made has been incomplete, and armed also with the knowledge, the hard-won, repeatedly demonstrated knowledge, that incompleteness is not a failure. It is the permanent, beautiful, humbling condition of standing at the edge of what is known and looking out at what is not. The wave is out there. 9,000 light-years of oscillating gas and dust and young stars rising and falling through the plane of the galaxy on a rhythm 70 million years long, carrying energy we are only beginning to measure, shaped by forces we are only beginning to identify. Part of a galactic system far more dynamic, far more alive, far more extraordinary than the static disk we long believed we inhabited. It was here before us. It will be here after us. And for one brief, extraordinary, statistically improbable moment in the history of the cosmos, we looked at it all and we knew what we were looking at. That moment is enough. That moment is more than enough. That moment is, if you sit with it long enough, perhaps everything.